what's on this board is a summary of the previous lecture. So there's an algebraic reductive group G over Q associated to a Shmurov variety, which will be called Y of some level K. The level K involves some primes, and we'll always have P in the level. And so the level is a product of this KV. So here KV is, as usual, compact, open in G of QV. And then we'll have some coefficients on the Shmurov variety, which are related to representations of the group G. So there's kind of an algebraic aspect, which comes from an algebraic representation of G. And then this will be a kind of KV invariant lattice. And we also have some smooth representation of all the KVs. This will be a KP invariant lattice. And then we also kind of allow some sort of a type. So we have smooth KV representations for each place V, and then some KV invariant lattice. And so using those representations, so at P, we can take the type and the algebraic lattice and tensor them together. And that gives us a representation of Kp that we can compactly induce to get a representation of G of Qp. And that's some kind of representation theoretic incarnation of a weight and some sort of level type data. And this is what sometimes people call like a locally algebraic type. And we can apply the conjectural functor to that to get a coherent sheaf on the EG stack kind of for G at P. And then we can also take all the types at the other ramified places and compactly induce them, and then take the conjectural coherent sheaf on the L parameter stacks at those places. And then you can kind of exterior tensor all those coherent sheaves together, and you get a coherent sheaf living over this product. And then there's a kind of a global to local restriction map that sort of takes a representation rho to the kind of tuple of local representations, the restrictions at all these places. And under that map, you can pull back this coherent sheaf to get something on the global stack. And so that's a sheaf on the global stack whose kind of, for example, its support is somehow measuring all the global Galois representations, which where, well, this guy will be supported kind of at rho, more or less, if this guy supported at the rho v's, and that will happen if each of these is individually supported at the corresponding particular rho v. And that will happen if there's some interaction. Well, that will happen if this rho v is in the support of this coherent sheaf. So there's a question of like which Galois representations on the space of parameters are in the supports of these coherent sheaves that these functors are producing. And there's a kind of a way to think about that because it's related to local Langlands questions. And I'm going to come back to exactly how to think about that. But kind of in some kind of grosso modo way, you know, rho v will be in the support of this guy. It will depend on the ramification. Because this is sort of only depends on like this guy, the kind of real input is this representation of Kp, which is some compact open subgroup. The question of whether rho v is in the support of this sheaf will be some question about the ramification of rho v. And it will be related to whether the ramification of rho v is kind of attuned to these particular types. So again, at L not equal to P, the amount of ramification is kind of bounded. Like if you have a p-adic representation of the Galois group of QL, and L is different from P, the amount of wild ramification is kind of bounded. And so that's why you only have these kind of smooth representations here. And when L equals P, if you have a p-adic representation of a local Galois group at P, the amount of ramification can be, the wild ramification kind of be infinite, and you can measure it with things like Hodge-Tate weights. And so you also have this algebraic representation that's helping you measure things like Hodge-Tate weights. So you have this guy, and then we make this conjecture that, sorry, somehow this is incomplete for some reason. So inside here, what's supposed to be there is the coefficients. And so the coefficients are like this. I'll just write them in with the same kind of notation. But what's happening is that we're getting we have representations of the level groups, and so we can use those to make a local system on this Shimura variety, and then we take coefficients in this local system. And what's written here is there's some kind of a shift, probably. In the case I explained for PGO2 last time, there was no shift, but in general, there'll be some shift, I think, related to this Shimura, this G, it says to a Shimura variety, implicitly there's some Shimura datum that I'm suppressing notation for, and that Shimura datum has an associated co-character, which is traditionally called mu. Mu is typically, in the case of PGO2, the mu is a regular co-character, but typically mu is not regular, and so there's some shift here that's sort of related to the kind of regularity or irregularity of mu. And so this conjecture is sort of telling us that we can compute the cohomology of our Shimura variety in terms of this data produced out of these coherent sheaves produced out of these fully faithful functor conjectures together with this local global map. So this conjecture is, one should think of it as aspirational in the sense that, of course, I think it's a nice conjecture, so I would love that ultimately it was like a kind of a tool that such conjectures could be proved and could be a tool to prove things. But at the moment, one should think of this as being sort of, as I said, like aspirational, trying to express how different structures should be related. Because as written, it has, it's a very, very strong conjecture and presumably very difficult to prove, because that's the kind of thing it will tell you. Kind of as I was saying, this guy will be kind of supported at Galois representations that have certain ramification conditions at these bad primes. So roughly this right-hand side will kind of detect all those Galois representations. And so, and then this conjecture will tell you that if you sort of have a Galois representation in the support of this sheaf, then roughly that Hecker eigenspace, the corresponding Hecker eigenspace on this side will be non-zero. So the conjecture will roughly tell you things like that, and that would mean that this conjecture includes modularity conjectures, like the Fontaine-Mesa conjecture just inside it, because it will tell you that kind of something on the right-hand side, the right-hand side doesn't mention automorphic forms or Shimura varieties. The right-hand side is just a thing you compute using spaces of Galois representations. But if it's equal to the left-hand side, it tells you that Galois data is actually living in the cohomology of a Shimura variety, and so that's telling you that some Galois representations are automorphic.
But the mu for the Shimura variety is entering also the definition of the rho.
Yes, that's correct. Yes. Yeah, so this rho universal is taking, again, let me suppress G hat versus GL versus GC. Let me just say G hat. But this stack is carrying a kind of a universal family of kind of G hat value Galois representations. And the mu of the Shimura datum gives you an actual vector space representation of G hat. And so using that, you can convert the kind of universal G hat representation into an actual vector bundle. At each point of X, a priori, there's kind of a G hat value Galois representation, but now that G hat is acting on a vector space via mu, and so you get an actual vector bundle. with the Galois action. And that's what I mean by the Rho universal. And so again, this conjecture will include all, well, roughly will include sort of all things like arthomultiplicity type conjectures and things like that as well, because it will be telling you, like it will include the fact that, you know, in a non-endoscopic situation, in the most kind of generic automorphic situation, the cohomology, a Hecke eigenspace lives only in the middle cohomology of a Shimura variety, and its dimension is exactly the dimension of the representation given by mu. But once you have endoscopy and other phenomena, that doesn't that's not literally true anymore, and so all that kind of information will be encoded in this conjecture. The one thing to say though is that, say for example, literally an arthomultiplicity conjecture would tell you about L2 cohomology of the Shimura variety, and this is about compactly supported cohomology. And I guess I don't know if there's a corresponding L2 version of the conjecture or not.
So in the case of modular curves,
yeah.
How far are we from the conjecture?
So as I also said last time, you can kind of localize this at you can sort of localize at pseudo, like kind of mod P pseudo representations, because the stack, the global stack X breaks up as a disjoint union of components labeled by mod P pseudo representations. And so then you kind of, so let me just write it underneath. So you kind of have RKC, YK, same local system, and then localized at the maximal ideal for some pseudo representation. So that will be conjecturally equal to R gamma on X, the stack, the connected component for that pseudo representation of the same thing. So for PGL2, or for modular curves, this is like this is probably known if theta bar equals rho bar is irreducible. I'd have to, I forget it. I mean, I proved a local global compatibility result for cohomology of modular curves, which essentially proves this statement, maybe with epsilon additional assumptions on the rho bar, which I don't remember exactly right now. Okay, well, there's a question of how, given that these fully faithful functors are these Gothic A's are themselves conjectural, so how can I make this claim that I proved such a thing like 10 years ago? So what I proved is a statement like this. So first of all, as I explained last time, when theta bar is irreducible, this stack becomes very simple. It essentially just becomes a deformation ring, and so this sort of stacky considerations go away. So this side is more elementary than it looks. I mean, at least this aspect, and so this R gamma and this X become more elementary than they would look. And then when you think about what this is, you kind of have to give a rigorous interpretation to what Gothic A should be. And but we know that it should be kind of recovering p-adic local Langlands when V equals P, and there is a p-adic local Langlands for GL2QP, and so that p-adic local Langlands appeared in my statement. And away from P, I proved my statement in terms of the kind of local Langlands in families that David Hellman and I worked out. And as Eugen conjecture, rather Eugen Hellman conjectures, and then I should say, so this was Eugen kind of conjectures that the local Langlands in families should be the L infinity for the functor Gothic A for GLN when L is not equal to P. Right, so Toby explained in his talk that when you have one of these fully faithful functors, one way to realize a functor is to have some kind of like bimodule L infinity over the parameter stack. So a kind of a coherent or pro-coherent sheaf over the parameter stack that also has an action of the p-adic group or l-adic group. And so David Hellman and I kind of conjectured some kind of local Langlands in family, and then David Hellman, Gil Moss proved that it exists. And then, well, for GLN, and then them and Jean-François Dart and others have gone further and are developing these local Langlands in families for classical groups. So that local Langlands in families is one way, one at least kind of conjectural way to kind of to produce an L infinity, and hence produce this Gothic A. So I kind of established this conjecture, I guess, interpreting the Gothic A in terms of known things like the p-adic local Langlands for GL2QP and the local Langlands in families. But if theta bar is reducible, there's sort of we have sort of partial knowledge. I mean, maybe so. Well, we're very partial knowledge in the sense that if you care about, say, using this conjecture to prove automorphy, Skinner-Wiles and then Louet-Pan essentially established automorphy theorems as strong as the more traditional ones for irreducible rho bar for reducible rho bar. So the kind of automorphic consequences of this conjecture are known. But if you want to have the conjecture itself on the nose with integral structures and everything, then I think it's kind of not known, but there's sort of, there's partial knowledge. And as I said in the previous lecture, it's related to generalizing computations in Mazur's Eisenstein ideal paper to kind of composite level and so on. And there are a lot of partial results about this in the literature, but it's far from known. So
can you remind the notation yk and xgqs in the conjecture?
Yeah, so yk means the Chamorro variety attached to G with this level. And the x is, so that's the moduli stack of Galois representations of the Galois group of Q unramified outside S. And they're going into, well, the C group of G. So which is basically the same as the L group of G, which is, more or less the same as the dual group.
There is no K there.
No, so there's no K. So on the left hand side there's a K. On the right hand side, right, the K is coming in. So in this sort of choice, like in some sense, the representations that are being fed into the Gothic A, since those are representations that are kind of that are compactly induced from the level structures, the K is kind of implicit on the right hand side in those coherent sheaves. So the K is not explicit, but it's implicit in some sense. Right, you're using the K to produce. You're using the K plus these choice of representations to produce the representations. So in fact, I can maybe, in some sense, we can kind of erase the K from this left-hand side too by going to infinite level. Maybe I'll do that in a minute. But I wanted to just kind of recall that if theta bar equals rho bar is irreducible, and let me just say and just to be concrete, since already the modular curve case is not completely understood and it's interesting to think about, let me just be in the modular curve case. Then we had this picture from last time where you have just now a universal deformationing of rho bar, just unrestricted, unramified outside S and unrestricted at S. And that sort of, and then, and maybe when I say irreducible, I should say irreducible plus kind of a Taylor-Wiles condition. So to do Taylor-Wiles patching, you need slightly more than irreducibility. So let me just, if you don't know what that is, then you don't need to worry too much. And if you do, then you do. So then we get this inclusion into a kind of part of the Taylor-Wiles method produces some kind of spurf of R infinity, which is something which contains spurf of R rho P as a closed subscheme. And this R infinity is by its kind of construction, the tensor product of local deformation rings together with some power series variables, which are neither here nor there. And so that maps to the product of these xv's, and that's versal, because this deformation ring is kind of a versal ring to rho v at this point. Sorry, this should be rho bar. This deformation ring is versal to this stack at the point rho bar, and so this product is versal to this product. And then these power series variables just add something smooth, and so that doesn't change versality. And the global stack is the deformation ring modulo a trivial action of mu2, where the mu2 is just the center of SL2. So it's just the kind of you have this irreducible rho bar, so the kind of automorphisms are just the center. And because I'm doing PGL2 on the automorphic side, it means I have SL2 on the G hat side, and so the center of SL2 is mu2. And as I said last time, very general principles will tell you that so again, when this sheaf on this stack, what does it mean to have a sheaf on this quotient stack? Sorry, it just means you have a module over this ring with a mu2 action. But since this mu2 is in the center, kind of very general principles will tell you this mu2 is acting trivially, so you don't have to really worry about it. So really, this is just kind of this guy.
So when you say general principles in this case, we don't mean something conjectural, right?
No, I mean something, I guess, conjectural. General principles of how these conjectures work.
But in this specific case,
well, again, the Gothic is somehow not defined. So, but I mean, somehow either the mu2 will be acting basically trivially, and then you will get something. If it's acting non-trivially, you'll be kind of getting zero. I mean, so you have to kind of imagine that the mu2 will be acting trivially, otherwise nothing will be happening.
The general principles then have to do with how we kind of normalize the Langlands correspondence in an L package so that it is.
Yeah, but this mu2 is, but it's somehow, it's kind of related to the fact that, say, in like an Arthur-type multiplicity formula, like the centralizer of packets plays a role, but the center of the group itself is always taken out.
Because we're looking at the quasi-split.
Yeah, so this mu2 is the center of the whole group. It's not the centralizer of some particular thing. It's a center of, well, it is a centralizer of a particular guy, but it's a centralizer of a non-endoscopic guy. So it's just the center of the group. So the center of the group doesn't kind of do anything. So this is this map F, but it's basically, you can kind of, since you can basically ignore this arrow, you can pretend this arrow is an isomorphism. The map F is essentially the composite of these two guys, and so the conjecture says in this case that again, I'm not, whenever I put this dash in the H1 or the cohomology, I just mean with the appropriate coefficients that I've been writing. I just don't want to keep notating them every time because they're a bit long to write out. But it's telling you this cohomology. So now we're kind of looking at this rho bar. And again, because this rho bar is irreducible, this modular curve cohomology completed at this rho bar or localized at this rho bar will just live in degree 1. So the R gamma kind of collapses to an H1. And it will say this H1 is equal to, well, we sort of have to do this versal thing and then do this inclusion. So for this versal guy, the upper streak and upper star are essentially the same, and then this inclusion will actually be LCI. That's kind of more or less part of the Taylor-Wiles method. And so again, the streak and the star are essentially the same. So you'll kind of get so I'm just using like my notation. I mean, like this computer science mode of just using your like what you wrote as your symbol for the variable. So inc is for the inclusion and versal is for the versal map. I think computer scientists generally find it like crazy that mathematicians just denote everything by like F and G and H instead of using strings that actually have a conceptual meaning. Like I think computer scientists give their variables strings, names that are strings that actually have a conceptual meaning. So so we're supposed to do this and then sort of tensor with this universal guy. And then, but again, what Taylor-Wiles patching does is it doesn't just give you this inclusion, it sort of tells you that, I mean, it gives you a path to go from this closed subvariety to this thing that it sits inside by adding auxiliary primes to the level of the Schmor variety. So that sort of in between here and here, there's a bunch of other row bars where you've enlarged the set S. And so you don't just have, so in Taylor-Wiles patching, you don't just have like one statement like this. You kind of get if you combine Taylor-Wiles patching with this equation, you get a sequence of statements like this where the level K is kind of getting larger. And in the limit, you kind of approach in some curious like non-canonical ultrafilter kind of limit, you go from here to here, and then so then the H1 becomes called M infinity. And you're applying, and so, well, when people don't write M infinity, they normally, this patching was traditionally thought of as being applied to types. And so they normally write down some kind of representation of Kp. So they'll tend to write things like M infinity of tau p tensor v chi 0 tensor. They'll write something like M infinity of the thing you induced, and you'll find that's equal to, well, the pullback of the A. And there's this row, but often when you make this M infinity, you pull out this row and you forget about the row. You just think about the thing in front of it. And so you end up with a formula like this. So this is related to kind of the famous, like, it goes back to Mesa of mob P multiplicity 1. Mob P multiplicity 1 tells you that a certain piece of cohomology of a modular curve has dimension 2. Not 1, but it's dimension 2 because it's a two-dimensional Galois representation. So the Galois representation appears once. So so this guy is kind of measuring some multiplicity in a way of this guy. And so the multiplicity, so this thing we kind of know, the multiplicity space in front of it is what's interesting. So that's what we kind of extract. So we extract this multiplicity space. And so this is sort of why, as I said last time, this is why this conjectural functor, or this is really a conjectural kind of collection of functors because it's kind of coming from all these, the p-adic Gothic A and then the v-adic Gothic A's. So this kind of sheaf, as we vary these guys, we're kind of exploring, and we could vary the set SF, we're sort of exploring how all these different conjectural fully faithful functors are behaving. And this kind of deduction from the local global compatibility conjecture is the basis for, well, one basis for believing that these conjectural fully faithful functors are kind of related to patching. So, so for me, that has a couple of kind of consequences, in a way, philosophical consequences, because everything here is about conjecture. So in a way, it's about philosophy, maybe more than mathematics. But so first of all, I'm not sure if, I forget if Eugen explained this in his talk, but there's sort of other ways to think about these fully faithful functors. Well, for example, like a lot of people were motivated by Vincent Laforgue's work. And then, of course, Laforgue was motivated in part by geometric Langlands. And then in Eugen's notes for this course, he also talks about constructing these fully faithful functors in different contexts using results of geometric Langlands. So, on the other hand, for me as a kind of like a modular curve number theorist, geometric Langlands is pretty far from what I have a good intuition for, but patch modules are something I thought about a lot. And to me, one thing that's just striking about this conjectural formula is that, although, I don't know, there's like a bunch of letters and maybe looks a little technical, it's kind of saying that there's some objects now in the kind of number theoretic perspective on the Langlands program, which in a kind of precise way is supposed to be both informed by the most number theoretic aspects of the Langlands program, which is Taylor-Wiles patching, and by, in some sense, the least number theoretic aspects of the Langlands program, which is the geometric Langlands. So those two things are the same. I mean, there's an equal sign here, so they're supposed to be the same. So, you know, experts in kind of like modularity, Piatic Language, and so on, and in geometric Langlands have for a long time tried to kind of talk and share ideas and communicate things, and it just wasn't clear that these 2 points of view in the Langlands program would really like do the same mathematics as opposed to just perhaps have conversations over lunch. But they now seem to, yeah.
If this doesn't drag you into talking about patching, can you explain, like in one phrase, why the row universal disappeared? Otherwise,
yes. No, it's just that you can kind of, it's just traditional to factor it out so that when you, instead of saying like some space is free of rank 2, you factor that out to just record the multiplicity space. So it's just the multiplicity space. It's almost by definition. Yes. Yeah. So,
is there a Hecke algebra action on the right-hand side?
I mean, not sort of coming from here, but rather like if you look at these compact inductions, they have endomorphisms, which are so each of these guys has an endomorphism ring, which is a kind of a local Hecke algebra, and that Gothic A is a functor. So that means that there's kind of a local Hecke algebras acting on the right-hand side, and they should match with the local Hecke algebras acting on the left-hand side. So, yeah. Like these compact inductions, the endomorphisms of a compact induction is a Hecke algebra. And so the Hecke algebras acting on the right-hand side, and of course exactly those same Hecke algebras act on the left-hand side, and this should be equivariant for those actions.
Maybe he was referring to the algebra outside S.
Well, outside S, yes, outside S, there's, there again, Hecke algebra is acting on both sides, because in some sense we could always enlarge S, just like if you have a prime that's not in S, you can just add it to S. But then what we're studying will be the situation where everything's unramified outside that S. And so you could kind of put in a factor for that extra prime, and you would have the compact induction from the like a hyperspecial maximal compact to the full group of the trivial representation. So you'd throw in an extra factor, you'd have a spherical Hecke algebra acting, and that would match with the spherical Hecke algebra acting here. So yeah, so at all the primes not in S, there'll be sort of spherical Hecke algebras acting on each side. And but in some sense,
purely Galois theoretically.
But so matching them will be related. So again, in Jinwen's notes for this workshop, he has conjectures where he kind of explains how like the global functions on the unramified component of a local stack of parameters should be identified with a spherical Hecke algebra. So that's how the kind of spherical Hecke algebras at unramified primes can appear on the right-hand side.
In the example you just gave, it's not so clear why one should use F upper shriek instead of upper star. Can you say something?
Yeah, so if you look at, so I think, so first of all, this use of F upper shriek instead of F upper star, I believe, is something that's been well understood in geometric Langlands for a long time. So I think that was sort of the first motivation for why that will be the correct thing. But also in an example where, so I briefly sketched this last time, but there's the example where theta equals 1 plus inverse cyclo. And in that case, when you look at x theta bar, so you get a kind of let me be a little vague, but you get kind of Eisen's. This stack will have, for example, here so first of all, this stack won't just be the kind of spec of a local ring modulo a mu2. It'll be have more stackiness, but it'll have kind of irreducible components that are labeled by the relevant modular forms that contribute to this residual representation, and sort of one of them will be kind of there'll be an Eisenstein component, and so from a Galois perspective, like for example, if you have some prime L in your level, then taking pth power roots of L, Kummer theory gives you an extension of trivial by cyclotomic, or hence of inverse cyclotomic by trivial. And so this Eisenstein component, for example, will have these Kummer will be kind of these Kummer classes. And so this so suppose that SF just had infinity P and 1 prime L, then there'll be kind of like just 1 prime L where you can make this Kummer class, and so you'll kind of might get, so this is supposed to be just a line. This is supposed to be like a one component of a stack, kind of, and this line is that's kind of like standing for the one-dimensional H1 that's spanned by that Kummer class at L, and so but that extension, that Kummer extension is locally at L. It's also the same Kummer extension, and so it's kind of Steinberg locally at L. So what I've drawn here is the kind of the local at L stack, kind of XL, and I guess I've drawn the kind of unipotent picture, and I think Jean-François drew some version of this picture in his talk. So there's kind of an unramified component here and a Steinberg component. And so this thing will this line will kind of map to this line. And when you, and then when you think about what the Gothic A will be, yeah, so maybe here I'm imposing a condition, which is I'm imposing a kind of L unipotent condition, so that I'm mapping to this kind of unipotent at L stack. So the relevant coherent sheaf will be what Xinuan called, and I think David Ben-Zvi and his co-authors call the coherent Springer sheaf. And the coherent Springer sheaf on this stack is a direct sum of the structure sheaf of the whole stack and the structure sheaf of the unramified. So the relevant A is equal to the structure sheaf of this whole thing together with the structure sheaf of just the unramified thing. And that's what you're then going to kind of pull back. Well, then you have to decide which pullback to use, which is your question. But the thing is that you use the Schrieg pullback, and the way you can see that works is that when you do the Schrieg pullback, this structure sheaf sitting here doesn't interact very nicely with this guy, which is mapping in vertically. And so the upper Schrieg really has higher cohomology, and that will explain, well, I mean, it's a very elaborate explanation and a conjectural explanation as to why the compactly supported cohomology has an H2. So if you did the upper star, already you wouldn't get H2. But here, the compactly supported cohomology, the F upper streak produces, in fact, the F upper streak will give you cohomology in sort of a bunch of higher degrees. But when you do this, when you pull them back, over here you'll get a complex which kind of has cohomology in a bunch of degrees. So when you do the R gamma, you kill off most of those degrees, but the H2 survives and you get a one-dimensional H2. But you also see that phenomena, that's only happening with this Eisenstein component. These other cuspidal components, they somehow, at least in characteristic 0, they don't hit, if you invert P, they don't hit this unramified line. And so they only will be in H1. So that's, and in general, that's the kind of thing that happens in this local to global map, is that in Taylor-Wilde situations or in more sort of situations, I think I said last time, studied by Berkler and Kissen, like very often one knows that this map F is a quasi-smooth morphism of derived stack. So it's kind of an LCI morphism. And it's kind of not going to be an LCI morphism when there's some kind of interaction between the way it's sort of not an LCI morphism is that in the local stacks you have a union of different components, and the global stack has kind of fewer components, and so the global stack only hits some of the components in the local stack, but it contains an intersection point with a component that's being missed. So it looks roughly like, one irreducible component embedding into a union of two irreducible components. And that's the basic phenomenon of non-LCI morphisms. But those intersection points tend to be points like in this case, this point is like trivial plus cyclo inverse. So the points where different components meet, they're basically kind of points where you're looking at maybe some unramified guys and you take some special limit where you can see that you can fit in a non-trivial n in the sense of a Wedeline n, and then you have another component you can move along where you've put in an n. So that's where these things meet. But from another perspective, having a Galois representation which emits an n looks like a Galois representation where you could put in a non-trivial Arthur SL2. And so the points where this map F is kind of not an LCI map basically are points where you could have non-trivial Arthur SL2 contributions to your parameter. And so you see, at least right now, I only see it in a very vague way, like what I'm telling you is basically what I see, that you'll kind of see that this side, for most kind of, if you localize at most points, it will just be living in middle degree, and you'll sort of see that for most Galois representations that appear in the Schmor variety, they appear kind of in middle degree with nothing very mysterious happening. But at kind of points where you can have a non-trivial Arthur SL2, then the cohomology becomes harder to compute and gets spread over more degrees. And so that's sort of related to this, at those points is F not being LCI and the F upper streak being non-trivial. But you have to do F upper streak to see that phenomenon, not F upper star. F upper star won't see that, I don't think. Okay, so yeah, is there a question?
Well, no, but since the DJ seems to be open to requests, are we going to see at all a discussion of the p-adic local Langlands correspondence?
Yes. Yeah. So, so maybe I want to just say that the kind of thing you can investigate with this formula and with variations of this formula is, like, suppose you are trying to do p-adic local Langlands, and you've convinced yourself that since the traditional methods seem to be like getting stuck, you should have this categorical perspective, and you believe these sheaves exist, and sort of how Toby and I and Eugen have that's the situation we've kind of found ourselves in. You'd like to know where these sheaves are supported. And again, you can see here that, I'm writing A, so it looks like I'm talking about an object, but this A had these inputs which are kind of varying. So this A is really kind of a functor. So we can imagine putting in different test objects into A, and then we get, then these things vary. Then we can try and think about where this is supported. So from the perspective of this equality and our, background as like patching number theorists, you kind of think, well, where are these M infinities going to live? And so you can think about, for example, in here, sort of instead of having something, so here these were lattices in p-adic representations, you could go to mod p coefficients. You can, I mean, there's a big tradition of studying cohomology of Chamois varieties with mod p coefficients, especially modular curves. The p-adic situation, in any case, if you reduce these lattices mod p, you get some mod p coefficients. So it makes sense to kind of put in mod p coefficients. And the simplest mod p coefficients to put in are maybe like trivial representations away from p, to kind of, so get rid of the contributions away from p, say, and just put in an irreducible representation at p. So you could imagine here taking kind of like kp equals, say, pgl2 zp, and all the kv are kind of pgl2 zv. But now we're going to have these acting on kind of the trivial. But here, have this kind of acting on some irreducible representation. These irreducible representations of pgl2zp, kind of with fp coefficients, they automatically factor, they're always inflated from pgl2 of fp. So really this is a pgl2 fp representation. So it's just a representation of fp 2x2 matrices. And in characteristic p, those are just low weight algebraic representations of pgl2. So symmetric powers with twisted by powers of the determinant, but with kind of low weight.
The coefficients are fp?
Yeah. Yeah, so irreducible over fp now. So kind of from a p-adic perspective, that's the kind of most basic building block to put in. Then you can imagine this lattice mod p is going to be some mod p representation, so it's going to be some successive extensions of such things, and then the p-adic guy is some p-adic limit of successive extensions of these things. So understanding these guys is kind of the building block to understanding these kind of things. And we can see, so that will mean we're applying our functor to the compact induction of this sigma bar. But there's a whole kind of philosophy of when this should be zero or not, which is the weight part of Serre's conjecture. So the weight part of Serre's conjecture is a conjecture which tells us that if you put in a mod p local system here, and you ask whether its localization at this particular rho bar is zero or not, that will depend in some way exactly on the ramification behavior of rho bar locally at p. So what one says is that, sort of the upshot is that what we see is that if we take this coherent sheaf for this sigma bar, that coherent sheaf should be supported exactly at the points in Toby and my stack, which emit sigma bar as a Serre weight. So again, if you've sort of never seen Serre weights before, that's maybe not so helpful, but if you have, that tells you a lot. But again, it's essentially, it means like at those rho bar which have certain ramification behavior. And because we're putting in a very simple representation, it turns out that we often know that these guys will be one-dimensional, or they'll be kind of like the fibers over each point will be one-dimensional as a kind of a mod p multiplicity 1 result. And so in fact, what we find is that for these guys, at least if this sigma bar is irreducible and it's not near the, so it's going to be like an irreducible representation of pgl2 in a lower alcove, and as long as it's not near the walls, then we'll see that this guy is a line bundle on its support. So, and then you can kind of figure out which line bundle it is, and that leads you into kind of mod p and Piatic Langulands again. So I want to say something about that in just a minute. But I just want to say one other thing is that instead of making the sigma bar as small as possible, you could also instead of shrinking our perspective to kind of these sigma bars, where we're going mod p and taking the smallest possible things we could plug in, we could expand it to kind of, in some sense, like the universal parabolic induction, which will be we could take kind of the group ring of PGL2ZP, so the kind of free representation of PGL2ZP, and plug that into the compact induction and then sort of think about that. And that will take us from finite level at P to infinite level at P. And so then we will be doing patched, we'll be doing like completed cohomology. And we will kind of get back to kind of the L infinity that Toby talked about. So we get back to kind of an L infinity having some connection to completed cohomology. And I guess like one reason, well, in fact, the reason I originally introduced completed cohomology was to help find a representation theoretic mechanism for studying eigenvarieties. And so once you have completed cohomology, you can take locally analytic, you can invert P, and then you can take locally analytic vectors and you get locally analytic representations of, say, PGL2QP. And then you can probe that space with different test representations. In particular, essentially with Verma modules. Well, Verma modules are representations of the Lie algebra, but they're sort of this sort of various ways parabolic induction and variance of parabolic induction due to all they construct let you convert Verma modules into actual locally analytic representations. And you can kind of probe the completed cohomology with these Verma modules, and that detects the points on an eigenvariety. And so it turns out that the eigencurve, for example, comes on it with a natural coherent sheaf of, well, the different perspectives, but one standard way people describe it is a coherent sheaf of rigid analytic modular symbols. So in any case, the eigencurve comes naturally not just as a curve, but a curve supporting a certain coherent sheaf. And so you can get that thing by as a sort of a multiplicity space, very similar to what's on the board, except that I go to level infinity and I probe with something more Lie theoretic, like a Verma module. And so that's where the rigid analytic version of the conjecture came from. So in Toby's talk, he had the Banach case, which is what I've mainly been talking about here, but also the analytic case. So the analytic case of the conjecture comes about from kind of just the same idea of probing the cohomology of a Shmur variety with different test objects, so sort of different local systems, or going to level infinity and then probing with different representations of the Piatic group, and getting multiplicity spaces that have some support, but then trying to understand how that support is really a purely local thing. So like in Sayre's conjecture, a priori, if you put in a weight sigma bar in that, like at the top of this board, we have this slot where we can plug things in. A priori, if we plug in this sigma bar, the condition for this to be zero are not made, a priori it depends globally on the global rho bar, but Sayre's conjecture tells us it actually depends only on the local structure of rho bar. So in general, the theory of Sayre's conjecture, of eigencurves, all kinds of different parts of the kind of number theory of automorphic forms, fundamentally have all been about various kind of coherent sheaf multiplicity spaces on various moduli spaces of Galois representations and trying to understand where those are supported. And as time has gone on, one has realized that basically those are always, support conditions are always determined by local conditions. And this Gothic A perspective is kind of, for now, the like ultimate distillation of how to think about these multiplicity spaces being coherent sheaves on some space of kind of Galois representations determined in a purely local way. Because we're actually going to these purely local Galois representations and trying to build the coherent sheaves directly on them. So, so that's sort of where eigenvarieties and the analytic picture kind of come into the story. And so again, this so the kind of questions that people have studied related to these M infinities and these kind of multiplicity spaces are things like the weight part of Sayre's conjecture. Of course, like the Fontaine-Mazer conjecture. So when I was studying the the local global this kind of conjecture for PGL2 that Sagru asked about earlier, I was interested in trying to prove cases of the Fontaine-Mazer conjecture. There's also something related to the weight-Padicès conjecture called the Broi-Mosaic conjecture, which also is studied, Mark Kisson studied using, again, kind of Taylor-Wells patching, and his perspective was one of the first things that made Taylor-Wells patching look like it was a functor, which was a key thing to make the left-hand side a functor, which is good because it's supposed to be matching with the right-hand side being a functor. And then Christoph Broi and Eugen, Hellman, and Benjamin Schran kind of, in this analytic perspective, studied another question, which is called Broi's Sokal conjecture, which is a conjecture, well, about Sokals of locally analytic completed cohomology, but it's also, more concretely, it's a conjecture about existence of certain companion forms on eigenvarieties. So for people who know about eigenvarieties, they know that eigenvarieties have various kind of twinning behaviors and companion form behaviors. And Broi's Sokal conjecture is some kind of ultimate distillation of when companion forms should exist or not. But so these are sort of some collection of things that have all been studied using this idea of probing cohomology with representations of the p-adic group and getting some kind of coherent sheaf that's like a multiplicity space and thinking about the geometry of its support and trying to draw conclusions. And so again, this local global compatibility conjecture and these Gothic A functors are supposed to extract everything we learned by doing this, encoded in some kind of coherent mathematical concept, and hopefully tell us how to go further. So, okay. I guess there's another board here. So Janos asked if we can do some Piatic Language, so we can. Somewhere here in my notes. Here we are. Good. So I want to try to explain it, at least in some fragmentary way, how this connects back to kind of mod P, especially mod P Langlands and related things. But I want to give you a sense of how it relates to this. So for the rest of the talk, I'm going to focus on this Serre-Waite story. And I want to begin by showing you something. I already wrote this down last time, but I'll write it down again and build on it. What some parts of the stack that Toby and I made look like. So one thing about the stacks of phi gamma modules that we made is that we basically made them in the kind of in the most obscure way possible, which is that you define, well, the stacks, maybe they're fairly natural, they're stacks of phi gamma modules. Thankfully, Drimfeld proved some theorems, generalizing Rene-Gruson type theorems that kind of let you see they are a stack with gluing properties in reasonable Grothendieck topologies. But it's pretty, at least to us, pretty far from obvious that they're formal algebraic stacks. And we prove that in the most indirect way that's possible, which is by really using Artin's axioms. So unlike in the case of the local parameter stacks for L not equal to P, where you can really sort of just write down a discrete model for a Wedelin group as you can just write down a finitely presented group whose profinite completion is a Wedelin group. And so then you can just study the representations of that finitely presented group, and you get a concrete representation variety, and then you quotient out by conjugation, and you get a very concrete quotient stack. So for V not equal to P, the parameter stacks are just affine modulo reductive, very concrete quotient stacks with lots of nice properties because of that. Like GIT applies to them, for example. Our stacks are not at all built in that way. They're defined as they're written, we just define a stack of phi gamma modules as a stack, and then to prove anything about their geometry, we end up using, we use Artin's axioms. And so it makes them look very, very obscure, and at first not so clear where they came from. On the other hand, I tried to explain in the lecture last time that the actual idea for these stacks to exist came from drawing concrete pictures in deformation rings. So they are, like, they're human comprehensible. They were kind of invented by drawing pictures on a board and just seeing how some things behave. They weren't invented by thinking about whether Artin's axioms would apply. So, so once you kind of know they exist, you can try to figure them out, and they're not so bad. So I want to explain how they look in this case, again, of kind of PGL2QP. So that will mean on the Galois stack side that I'm doing the stack Toby talked about for GL2, so two-dimensional representations of GQP, but I'm fixing the determinant to be the cyclotomic determinant. And so we have the stack. So this is the kind of D equals 2, and as I just said, determinant equals inverse cyclotomic. And it's a union of, and we can look at the underlying reduced. So again, this stack has a kind of a mod P algebraic stack as its kind of skeleton, and then it has all these formal directions, kind of like the muscles or the flesh or whatever coming off this skeleton in these formal directions. And so this underlying reduced is just the kind of algebraic skeleton of the stack, where you get rid of all the formal directions. And so it lives in characteristic P, and it's a union of components. So what Toby said was that they were equidimensional, of dimension 1 in this case. But we can say exactly what they are. So they're a union of all these weights, basically, of components, except because I fixed the determinant, there's a slight wrinkle. So let me just say it this way. So these, as I said, these weights are given by kind of just small weight irreducible representations of PGL2. So they're symmetric powers up to the P minus first symmetric power times the power of the determinant. Then the whole central character should be trivial to match with this condition. So that means this A is probably forced to be one of two possible values, but I'm not going to worry too much about it. And so away from, for the weights that are not of this form, you just get a certain irreducible component that I'll call X sigma bar. And then you also get, for the weights that are of this form, you get two components that are kind of somehow unramified twists one of the other.
Sorry, how many weights does this union have?
I think 2, because the central character has to be trivial. So A is probably either 0 or P minus 1 over 2. So probably here, A has to be one of these two values. Anyway, I'm not going to think much about these components. So these components kind of intersect the components where sigma bars is one-dimensional, so trivial up to twist. And that geometry looks a lot like the geometry of this picture. So somehow the extreme edges of, like, the 0 and P minus 1, which are the kind of extreme edges of these sigma bars, they behave quite a bit like the L not equal to P case. But they're kind of really the new p-adic or mod P phenomena are happening for all the other weights, where you see things that are not happening in the L not equal to P case. So those are the cases I want to think about. So I want to think about, so I want to choose some sigma bar. So it'll be some B symmetric power tends to some determinant of A. And again, I'm probably going to exclude, I want to exclude some extreme cases. So for some of what I say doesn't need this, but some will, so let me just do it. So I want to tell you what this X sigma bar looks like. So this X sigma bar, most of the points on it are reducible Galois representations, and they look like the following thing. So I'm going to use a notation in our notes. So lambda sub t is, the lambda just means unramified. So lambda is the same as unramified. So it's the unramified representation that sends Frobenius, or maybe geometric Frobenius, to a parameter t. And then omega equals mod p cyclo. And then here I have omega to the a plus b. And then I have an extension. I have 0. And I have lambda t inverse times omega to the a minus 1. And again, there's some condition which means this will have cyclotomic determinant. So this guy having trivial central character exactly makes this guy have cyclotomic determinant. When you look at these things, it's a bit of a mess. I mean, there's A's and B's everywhere, so it's useful to think that kind of the twisting doesn't matter too much. So you can just kind of pull out a kind of determinant. So you can pull out this guy, and then you have lambda t, and then you have omega to the b plus 1 extension, lambda t inverse. And that's not too bad. And that's sort of basically the hallmark of how weights should work. Here you have sim b. So you should imagine like maybe b is k minus 2. So sim k minus 2 has to do with weight k modular forms. And here you have cyclo to the b plus 1. And if b is k minus 2, this is k minus 1. So weight k modular forms, you know, if they're like ordinary, for example, the Galois representation locally at P on inertia looks like trivial and cyclo to the k minus 1. So that's the kind of numerology that's happening here. So so that's what I've written there is a family. Like I said last time, you know, if we write down on a board, in mathematics, if on a board we write some expression that has symbols, then we've written down a family. So in this expression, there are sort of two symbols. There's a letter T. So there's a kind of GM, you know, a non-zero number in this family. And there's also this star. And as we also kind of, Toby and I have both remarked, these extension classes are one-dimensional, like the x1 of those two characters is one-dimensional. So that star is really living in a one-dimensional x1. So this family is living over kind of a GM cross an A1. The star is a point in A1, and the T is a point in GM, except there are some symmetries. So it's a GM cross A1 modulo a torus, because there's a kind of a conjugation symmetry. But I won't write it on the board yet. It'll come on the board in just a few minutes. But what I first of all wanted to talk about is the fact that, so this is supposed to be some kind of wiggly arrow that kind of goes down the board. And what this wiggly arrow is doing is there's a specialization where we specialize star to 0. So that wiggly arrow kind of starts with the family, and then we specialize star to 0, and then we get to like lambda t omega a plus b. I mean, I just put star equals 0, lambda t inverse omega to the a minus 1. And then I can factor it a different way. I can pull out omega to the a plus b, and then I can put lambda t 0, 0, lambda t inverse. And here I have omega to the p minus 2 minus b. And this guy is also a specialization to star equals 0 of the following thing, which is lambda t omega to the a plus b. I'm going to put in plus 1 and then minus 1. That's for reasons I'll explain in a minute. 0, lambda t inverse omega to the a plus b plus 1 plus, p minus 3 minus b. The point is, what I've done is I've just put the extension in the bottom instead of the top. And so this is supposed to look analogous to what's on the top, except it's kind of flipped. And this guy is now playing the role of the a minus 1. So this quantity minus 1 is a minus 1, and this is like the a plus b. So that thing was attached to that Serre weight sigma. This guy is attached to another Serre weight, which is called sigma companion, the so-called companion weight, which is, we just read it off, and it's sim p minus 3 minus b of fp squared, tensor determinant to the a plus b plus 1. So what I've done is I've taken a family of row bars that have Serre weight sigma. I've kind of specialized to a particular locus in the family. So again, this family depended on two parameters, the t and the star. And I've left, the t is kind of still variable, but I specialized to the star equals 0. And now I've generalized again, but in a different direction in our stack. And so geometrically what I've done, so now let me kind of try and draw the geometric picture as best I can. So this is supposed to be a GM. So this is a line with a circle with an origin removed. So that's a GM cross an A1. And now, maybe in a different color, what I've drawn now is another thing. So this is kind of this is open in X sigma, and this is open in X sigma companion. And they're meeting along this GM, which is when you have a t variable, but the star variable has been set equal to 0. And so that's kind of, so that's a typical picture of how these components meet. Now this is not the entirety of the X sigma. There's also, for this Serre weight sigma, there's an irreducible representation that has this Serre weight as well. And so that kind of is, basically corresponds to setting t equals 0 and putting in the dotted line, except the origin itself is missing. So you get a punctured A2. And then again, this X sigma co has sort of has an extra point in it, which is an irreducible representation. But it's not the dotted line I've drawn, because you can see that the parameter that X sigma thinks of as being t, the X sigma co thinks of as being t inverse. So the X sigma co, the extra kind of point on X sigma co is kind of living at infinity on this GM. So I would have to kind of draw it somehow there. So that's how, and then but along this dotted line here, that irreducible representation has yet another Serre weight, and so like another intersection this way, and this orange dotted thing has yet a different Serre weight. My mental picture, I think of like those child's toys where you have these squares with slots and you can kind of slot them together and then you can build these kind of configurations. So that's kind of how this thing looks. But the nice thing is that for the sigma in this generic range, for this B in that range, what's on the board, literally these are, so this thing is literally open in this reduced. Like this guy is open in X sigma, but it's not open in the whole X reduced because it has, it meets this other component. But this union is open in the whole thing. So what is this guy in formulas? In formulas, this thing is a GM kind of with parameter t. And then we have these kind of two A1s that meet at a point. And so you get kind of two lines crossing, so a pair xy with x times y equals 0. But that thing is modulo a GM. So if you call the parameter on this GM u, then you have u times x equals u squared x, and u acting on y is u to the minus 2 of y. So it's a GM product two lines crossing, but the two lines crossing have a torus action. And the weight 2 is coming about because that this GM is really the diagonal GM in SL2. And the star is really the upper triangular star in SL2, and that's how GM acts. And one is upper triangular and one is lower triangular, so you get a 2 and a -2. Okay, so wait, that's the one I want to go on. So I have to try and finish up. So I want to so luckily I'm close to done with my notes too. Convenient. So I want to explain how. So what I want to tell you is I want to tell you what this is. And so it turns out that, again, this X sigma bar, at least when we have that condition on the sigma bar, that can be, is exactly all the rho bar whose say weight is sigma. And so this coherent sheaf will be supported exactly on that X sigma bar. Sorry, X sigma bar. And by sort of no mod P multiplicity 1 theorems, it has to be a line bundle. And the question is, which line bundle is it? And well, that component, well, there's an extra point. As I said, there's this like irreducible point, but if we kind of, that doesn't really affect the computation. So on A1 cross GM, which is what that white component up there is, every line bundle is trivial. But on A1 cross GM mod GM, a line bundle will be the trivial line bundle, but then with a weight of GM. So when we try to figure out what line bundle this goes to, we have to figure out what weight to have GM act by. And so, I just want to, so first of all, I should say that in this case, using kind of measures like D natural box P1 ideas, Toby and Andre and I have constructed this A, and so there's an answer to this, to what you get. But I want to show you how you can figure it out without having to compute anything complicated, using kind of more elementary reasoning, and then and some Occam's razor, and then how to generalize to other contexts. So I just want to try and finish up now in the next kind of couple of minutes. So it turns out that basically we know this is a line bundle on a certain support by patching. But patching can never tell us what line bundle we get, because if you have a line bundle on a variety, when you pull it back to the local rings of the different points, all you know is that you get a free sheaf of rank 1. You can't tell what sheaf you get by pulling back to versal rings. So we can't compute what this is in isolation. But so we're going to compute it by computing it in conjunction with the patch module or the functor for the companion weight. And so here's kind of the ansatz is that we're going to assume that the formula doesn't depend on the weight. So this is going to be something on kind of X sigma bar, so the structure sheaf with some twist that I'll call M, and I'm just going to assume that whatever twist you have is independent of the weight. Which is, somehow, I don't know, you write in a formula, like the components X sigma, their geometry doesn't depend on the weight, they all have the same geometry. I don't know, like if your weight is like B equals 13, like if the prime is sort of 60, I don't know, 61 or something, and your B is 13 and mine is 15, like why on earth would your twist be different to mine? There's no real reason to think it would be. So it's sort of a reasonable ansatz to assume that this is the same. And so then the interesting thing that happens is that these two guys emit a non-trivial extension. So they emit a non-split extension. And so you can apply the functor to that non-split extension. And when you apply the functor to that non-split extension, well, again, by general principles, you get a Cohen-Macaulay sheaf supported on the union of those two guys. And by fully faithfulness, a non-split extension is not split. So that Cohen-Macaulay sheaf cannot be the direct sum of the structure sheaf on each component. So on two lines crossing, the direct sum of the normalization is one Cohen-Macaulay sheaf, and the structure sheaf is the other maximal Cohen-Macaulay sheaf. But if you had the direct sum of just the direct sum, if you were on the normalization, that extension of sheaves will be split, and so then the extension of representations will be split because this A is fully faithful conjecturally. So if you have a non-split extension, you have to get a non-split sheaf, and so that means you get something on that union with some twist, and when you restrict it to the white locus, you'll get we're assuming you get this guy. But then, so therefore, just from that, like the M and the N have to match. But when you look on the orange locus, so the first thing that happens is that, right, the GM, as I said, the T on one side is a T inverse on the other. So on the orange locus, this twist by N looks like a twist by minus N. But on the orange locus also, the kernel, when you take the structure sheaf on that guy and you restrict to the locus where y equals 0, which is what this is, the kernel is generated by y. And y is in weight minus 2. So that gives you a 2 here. But that has to equal O of x sigma bar co twisted by m. So therefore we see that but now is it 2 or minus 2? So now I have to cheat. I think it should be a minus 2 because y is in weight minus 2. But let me check. Yeah, it should be minus 2 because y has weight minus 2. So we get minus 2 minus n is equal to n. Therefore, n equals minus 1. Therefore, m equals minus 1. And so you see that you've kind of computed what sheafs are, where the sheaf has to go. Where these Serre weights have to go. The Serre weight sigma goes to a line bundle on the component x sigma with a twist by minus 1. And then this generalizes to any, so just to finish, to say that this generalizes the PGO2 of QP to the F. That the Picard of x sigma, if this sigma bar is sufficiently generic, is equal to z to the f. And you can try to compute what the functor, of course you don't have a functor in general defined there, but you can try to start building a functor. And you can begin by kind of assigning you'll send this to the structure sheaf on the corresponding component with minus 1 in every slot. And with this definition, you can check a lot of things. So you can check that the endomorphisms match on the, so you can check that the endomorphisms match on the two sides. You can check that the extensions match. We're in the process of trying to check that higher extensions match. And so this board is kind of, sorry, it's going to take even more time to write out the list of names, but it's Anna Karyani and myself, and Toby, and Michael Harris, and Bao Lahong, and Brandon Levin, and David Sabat. We kind of have a working group working on this. But so we're kind of in the process of checking that higher x match on each side. And there are other tests you can make for various, they're non-trivial intertwiners and so on the representation theory side, and they appear on the geometry side. And then there are situations when some intertwiners don't exist on the representation theory side, and then those don't exist on the geometry side. So we've checked that with this definition, we've checked sort of fully faithfulness in both like positive and negative ways, both on HOMs and on derived HOMs in lots of different contexts. So I'm absolutely convinced that this functors exists, that the conjectures are true, and that that's the formula. And one thing I want to point out is that it's completely uniform in F. So unlike the more classical ways of formulating p-adic local Langlands or attempts to formulate them where there's no uniformity between GO2 QP and GO2 of QP squared or something, here it's completely uniform. Just the difference is that the geometry of the stacks becomes more complicated. So these are not affine mod torus. They're quasi. If you throw in that extra component, I said it was A2 minus 0 mod torus. It's quasi-affine mod torus. It's outside the realm of GIT. There are no associated moduli spaces, for example, beyond the case f equals 1. So the stacks just have a worse geometry, and so that's what's kind of making the coherent sheaves behave more strangely, and so then kind of by virtue of the conjecture surely being true, that's what makes the representation theory be harder to understand for QP to the F. But it's not, but the kind of the basic building blocks behave in the same way. So in particular, you can kind of start computing, I'm sorry to be going so long over, but just something I promised some people I would say is that you can apply this to Broipascunus constructions. And again, you kind of you start to understand what happens with Broipascunus construction. Like why certain representations get singled out and other ones don't. And you see that for QP to the, already for QP squared, this functor becomes quite derived. But you also see, like in Broipascunus, some of you will know that there's kind of a difference between the f equals 1 and f equals 2 case. Is in the f equals 2 case, when they draw certain diagrams, there's a non-trivial kind of loop that lets you get non-trivial parameters, and you get whole infinite families of reps depending on parameters. So in our context, the analogous thing will be that instead of having 2 components meeting, you have 4 components meeting around a deleted point. And if you delete that point, there's a non-trivial Picard. You get a GM inside a Picard. And that gives you some line bundles that give you coherent sheaves. And so that GM, for example, matches with a GM of Broipascunus parameters. So all the kind of complications in the representation theory for like GO2 of extensions of QP should just be kind of subsumed or explained by the complications in the coherent sheaf theory. But the basic objects are the same. You have this functor Gothic A that takes a kind of the Sayre weights to these very explicit line bundles. Then you just have to kind of build everything. So I should stop.